this presentation, we're going to look at the geometric series and its sum. Now, before we talk of a series, we must first of all understand the concept of a sequence. In simple terms, a sequence is a queue of numbers. Let's say where there's a first number, let's say A0, A1, A2, and so on. Now, to get a geometric sequence, we must have what we call a geometric. To get a geometric series, we must have what we call a geometric sequence. So when we say that a sequence, like the one given here, is geometric, we would say the sequence is geometric when given two successive terms, an and an plus 1. That is one term after the other, one term of the other. We have the condition that an plus 1 over an is a constant, and that constant in this case is called a common ratio. What does this mean? This means that if we were given a term of a geometric sequence, we can get the next term by just multiplying the given term by r. That is an plus 1, which is next after an, is equal to an times r. We see this from the above ratio. So if all the terms of the sequence satisfy this condition, we call that sequence a geometric sequence. So a series basically is what you can refer to as an infinite sum. In this case, if we take all the terms of the sequence and add them, let's say a0 plus a1 plus a2 plus dash dash an, and you can abbreviate this using this notation. Let's say I equals to 0 to infinity of an. Then we talk of a series. Now, what is important in relation to geometric series, we must understand basically how this series comes about and when is it convergent or divergent. Remember, note that here we're talking about an infinite sum. Now as we're adding infinite terms, what is possible here? We can get this sum this series being divergent, in other words diverges, or we can get it being convergent, can converge, or say converges. So what is important to know, when does it converge and when does it diverge? And when it converges, basically this means that the sum is approximately equal to a finite, is equal or approximately equal to a finite number. Now let's look at how first of all, before we can get to the sum of a series, we start at partial sums. Let's say partial sum. A partial sum basically is a sum of, let's say, first n terms, like Sn equals to a0 plus a1 plus a2 plus dash 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 plus an minus 1. Now, if we recall, we go back to this relationship of terms. We should understand that the first term here is a0, the following is a0 multiplied by r, followed by a0 multiplied by r to the power 2, and then the last one will be basically a0 multiplied by r to the power n minus 1. So that's first term. Now, the most to understand this thing, we would like to have an expression for Sn, which is the partial sum. In this case, let's consider multiplying Sn by the common ratio r, which will mean that we multiply each and every term here by r, which will give us a0 times r plus a0 times r squared plus a0 times r cubed plus dash dash plus a0 times r to the power n. I hope we understand that. Now, manipulating these two expressions, we can basically say let's separate let's separate r times Sn from Sn. We'll write something like this. Then if we subtract this row from that one, we can see that there are like terms there which basically are going to give us 0. Like for example, this one and this one is going to add up to 0. The following two also are going to add up to 0. This one with the next one is going to add up to 0, and this last one, the first row, is going to make this 0 with 1 before the last term, which means we're left with this first term and this last term of the second sum. So in this case, we're left with the a0 minus a0 times r to the power n. Now this expression is very important because it's going to make us arrive at the expression for the partial sum. On both sides of this equation, our formula, we've got a common factor. In this case here is a0, which is the first term of geometric series, and the side is Sn, which is the partial sum. So we can say Sn in brackets 1 minus r, and the other side a0 in brackets 1 minus r to the power n. This results in that Sn is equals to a0 brackets 1 minus r to the power n over 1 minus r. This is a very, very important expression because it's going to make us arrive at the sum of the geometric series. Now let's look at how we can get the sum of geometric series starting from Sn equals to a0 1 minus r to the power n over 1 minus r. We must understand that the sum of geometric series now will be the sum which we get when we add a0 plus a0 times r plus a0 times r squared plus dash dash up to infinity, which will be the sum of the series from I equals to 0 to n of a0 to the power times r to the power I. So first of all, we must consider two cases. That let's look at the situation where r, the absolute value of r, is greater than 1. If in this expression the absolute value of r is greater than 1, if we take powers of r, n powers of r, it is clear that this sum, these powers are going to grow to infinity, which will basically, if we analyze closely, we see that the whole sum then will be infinity, which will mean that the series will diverge. On the other hand, if the absolute value of r is less than 1, if we now take n powers of r, because the absolute value is less than 1, as n increases to infinity, they say n here is increasing to infinity, the whole power basically is going to shrink to 0. You can take an example of, let's say r is equals to half. Then if you successively increase the power of r from 0 towards infinity, you will see that half to the power n, as n is going to infinity, this will go to 0. So what does it mean for our expression there? Then it means that as n is going to infinity, when absolute value of r is less than 1, this part here is going to shrink towards 0, which means essentially we're going to have s at infinity. Now is the sum of the infinite series is going to be a0 over 1 minus r. Why are we arriving at that? We're arriving at that because if we let n tend to infinity, we obtain the series. Now as n tends to infinity, these powers are going to shrink to 0, being negligible. So once it's negligible, we can ignore that term. Then we're left with a0 times 1 over 1 minus that. So in this case now, we conclude that the sum of a geometric series a0 plus a0 times r plus a0 times r squared plus a0 times r cubed plus dash dash dash, the sum is equals to the first term over 1 minus the common ratio. In this case now we can say the geometric series converges to the ratio of its first term over 1 minus common, as long as the absolute value of the common ratio is less than 1. Now what is important here is how are we going to use this in solving some problems. So to highlight a few important facts here, I think you must notice that the geometric series is characterized by a common ratio and common ratio r, and that common ratio will make it diverge when the absolute value of r is greater than 1, and it will converge when the absolute value of r is less than 1. And the sum of the geometric series basically is given by the expression we've arrived at here. In the next presentation about this, I'll give you 1 or 2 examples to see how you can use this in solving some problems. I'll stop there. Thank you.